Hi, everybody. I'm Matt. I work at Netflix, and I made PigPen. So what is PigPen? PigPen is MapReduce for Clojure. But I don't really like to think of PigPen in terms of MapReduce. I don't want to write mappers and reducers. I don't want to have to think about Hadoop jobs and stringing data between them. Really, what I like to think of PigPen is as distributed idiomatic Clojure. I want to write code that looks like normal, everyday Clojure that you would run on one machine, and then I want to take that and I run it on thousands of machines. A lot of times when people think of MapReduce, they think of queries like I want to execute one query or I want to join these two tables together. PigPen is more about data flow. I want to take a bunch of different data sources. I want to map over them, filter them, and then join them together, group by, and then maybe join in some more data. I want to describe a graph of operations that I want to happen. PigPen is about iterative development. In a lot of the MapReduce tools that I've used before, there's very long cycles. You have to write a big script. You don't really know what it's going to do. If it's going to work, then you go run it. A couple minutes later, you get back some results, and it most likely won't work. With PigPen, I want immediate feedback, like we're used to in the Clojure REPL. PigPen is about unit testing. There are some techniques for unit testing MapReduce stuff, but a lot of times you end up having to put sample data into a file, run your script, and then get data back on the other side, actually read it out. I want unit tests like Clojure has unit tests. And with that, I want generative testing. I don't want to just have a static set of data going in. I want to be able to come up with generative tests for my PigPen queries. PigPen is composable. I don't want to write a large monolithic script and then submit that, and if I need to make changes later, I have to not only change part of the script, but other parts in there. I want to be able to have independent functions of logic. Just like you would in any other Clojure program, why should we expect any less for MapReduce? I want branching, I want looping. So I want to be able to conditionally run something in a script. I want to loop over things with different parameter values and parameterize my script. These things sound very simple, but in a lot of other MapReduce languages out there, you don't really have these constructs. I want it to be parameterizable, and I don't mean string substitution. A lot of scripting languages call that parameterizing, and doesn't really count. I want to actually pass in a chunk of data and work with that chunk of data. And of course, I want it to be massively parallel. I want to take my code and I want to run it on thousands of machines, tens of thousands of machines, hundreds of thousands. PigPen does use Apache Pig, but it uses Apache Pig in the way that Clojure uses the JVM. It's a host system, it's a host language. PigPen is not for writing and curating Apache Pig scripts. I asked myself this question a lot when I was making PigPen. I was like, there are dozens of other alternatives. Do we need another MapReduce language? And what I came to was, if you know Clojure, you already know PigPen. So who in here knows Clojure? You know PigPen. And I'll show you some examples. This is an example function here and the corresponding unit test. Pretty simple. It's kind of a nonsensical example. We have a function, take some data, assume it's just a sequence of numbers. We increment them, we filter them, we group by them, and then we have a mapcat operation. On the other side, we have our test. We define our data, whatever we want our input data to be. We call our function, and we get back a set of values. This is what the same query looks like in PigPen. Just not much different there, so I'll highlight it, make it easy for you. In the function, the only thing that's different is we bring in the PigPen namespace. And then Pig has map, it has filter, it has group by, it has mapcat, it has dozens of other operations that are all in Clojure core. The test is only slightly different. We need to wrap our data to make it look like a PigPen expression. So that's the pig return function. And then PigDump takes our PigPen expression and actually evaluates it and gives us back the data. Wouldn't have a talk about MapReduce without word count. So, yep, here's word count. The usual example for MapReduce. In this case, we have our word count function. Take some lines, we map cut over the lines. Each line, we split it, we do some normalization, et cetera, et cetera. What's different about PigPen is we don't have to define our tokenized function somewhere else. You can if you want to, but a lot of simple functions, it's a lot easier to just put them in line just like you would any other Clojure code. So we define our function that takes a line and does that. We group by identity, because at this point we just have a sequence of words, so just group by those words. And here you can see this is just Clojure core identity. We can use any Clojure function we want as our group by function. Then once we have our words grouped, it returns kind of, think of it like if you took a map and called seq on it. So you get a sequence of tuples, each one with the word that we grouped and the occurrences. So if you had a bunch of foos in your data, the word would be foo, and occurrences would be a sequence of foo, foo, foo. To count, we just use Clojure core count. You could do whatever else you want in this function. I'm just throwing it back into a vector of word and counting the occurrences. Notably absent from this word count example is anything to do about where the data is coming from or where the data is going. And that's intentional. I'll talk more about that later, but to actually use this, what do we do with our word count function? We take it and we make a word count query. So here is where we're loading data from a TSV file. We're using the threading operator to call our word count function. And then the output of word count, we're actually going to store that into another TSV. These things are new. These you don't have in Clojure core, but the Clojure core concepts didn't translate as well with loading or storing data the way that Hadoop does, so have a little bit difference. The nice thing about it is we've abstracted the actual word count business logic from the business of where am I loading my data, where am I storing my data, anything else. And this allows us to do a lot of different things with it. You don't necessarily have to abstract those things from yours. These are just Clojure functions. You can put them together any way you want. It's just a good idea. So what do we do with this? Oops, wrong way. So with this, we call our word count query. We give it the actual locations, input TSV, output TSV. Obviously, yours would be different. Then we take that query expression and we write it to a script. And this is going to give us an Apache Pig script, which you can take and just run on any Hadoop cluster. A lot of people use Pig, so it's a fairly known system of how to use it. You don't really have to look in this script. You could. It's just your Clojure code kind of in a Pig script, but it's up to you. So that's how you take it and run it on thousands of machines. But really what I want when I'm running MapReduce is to be able to quickly iterate and know what my script is going to do. I don't want to have to take it and run it on a cluster somewhere. So PigPen and the REPL. So as you saw earlier, we had our unit test. And we can return data. And this is as if I had a file somewhere. And on one line, I put this string. And then on the next line, I put another string. And would have loaded that. But in here, I can mock out my data much more simply and do it right in the REPL and define this as my data. I can then call our word count function, which didn't have anything to do with loading or storing data, conveniently, and then call this, use the PigDump operator to actually execute the expression and return the data right in my REPL. It doesn't go somewhere else. It doesn't go to a console. This is actual live data, real data that you can now interact with. With that, we can wrap this into a unit test. You could make it a generative test just as easily. These are all just functions that you're using to pass data through your actual logic that you can now run on thousands of machines. So how does all this work? We start with your PigPen code, which is really just Clojure code. in a slightly different namespace. Except that when it's executing, when you're actually calling pig map and pig filter, you're not actually doing those operations. You're building up an expression tree. This expression tree builds up as you compose these operations. It has the store, points back to the map expression, points back to where it got its data from, so you get back to where the data is all coming from. Then we take this abstract expression tree, and we optimize it. Say, hey, you loaded the same data twice. Combine that together. You loaded the same data twice over here. Load that combine that together. We have this DAG that basically explains what we want to do with our data. At this point, there's really nothing to do with pig involved here. It's all just kind of an abstract Clojure expression tree of how do I want to process sequences of data. From there, I can sequentialize these. Say I know I want the order to be, we need to load the data before we store it. I need to actually perform my operations before I do anything with it. From there, it's a pretty one-to-one correspondence. Pig has map, pig has filter, pig has group by. So you can generate all of these commands as scripts, and then take your script and run it on Hadoop. Pretty easy to do. But we're not done there. We can take that DAG and we can do other things with it. Right now, I'm converting it into RX. You don't need to know anything about RX to use this. RX is reactive extensions. It's a way to take a DAG of operations and execute them and kind of say, I want to subscribe to the bottom one, and then that propagates its way up through, and then the operations start pushing data back down through. It's a nice way to do asynchronous operations. It's very similar to core async. Core async didn't exist when I originally wrote this, so that's why I used RX. But ignoring the details of RX, this is actually what's powering the data into the REPL. And this is how we can go from immediately getting data back from the sample data, run it through our logic, and get it back in the REPL. We're not compiling it to a script. We're not starting up another JVM. We're not doing any of the normal things that a lot of other MapReduce frameworks generally do to run this and get you back your sample data. Joins, in the traditional MapReduce or SQL or any sort of relational sense, didn't exist in Clojure. So I came up with a new syntax for it. Join basically takes a set of relations, assume left and right or other PigPen query expressions, and then you specify a function that you want as your key selector function. So assume left is a sequence of maps, have a keyword A in them. So we're going to pull out the A element. Let's assume right is a sequence of vectors. Pull out the first element. And any time those match up, we're going to join them together and call this function that takes an L and an R. And basically, we take every element from left that joins and every element from R, the right that joins, and call this function. Right now, I'm just dumping it back into a map. You'd probably want to do something more intelligent with it, but it's just for demo purposes. Outer joins are a common thing in relational databases. So in here, instead of doing like a left outer, right outer, and that gets confusing, you can just mark relations as optional or required. It makes it a lot more sense when you get into more than two relations that you're joining together. You can also tell it how many machines you want to run this code. Pig, by default, will try to figure it out, but it's not very good at that job. So a lot of times you want to explicitly tell it, I want 1,000 machines for this. And that's really easy to do, just passing in options to the join. Similar pattern is cogroup. Cogroup is very similar to a join, except that it doesn't flatten your data. So say I have in my left thing a bunch of values with that same key A, and a bunch of values in the right with the same first value, a bunch of joins that would happen. A cogroup is going to take all of those and give them to you all at once. So K in our combiner function is the key that it joined on. L's is all of the elements in the left-hand side that matched, and R's is all of the elements in the right-hand side. Again, you can do whatever you want. You can flatten them, aggregate them, mash them together. In here, I'm just throwing it into a map and you can do whatever subsequent step you'd want. I also, in PigPen, wanted to close over data, and this is how we parameterize functions. I have a function foo here that takes a parameter p and some data. I'm assuming data is another PigPen expression tree of other PigPen expressions. Then we apply map to it. What's interesting about this is our function foo, the threading data through map, that all happens locally. That all happens at script generation time. That p is present then. Our function of x, where we multiply p and x, that's actually what's running on the cluster. So what I'm doing for you in PigPen is trapping whatever the current value of p is. Of course, it needs to be immutable data. You can't pass an atom in here or a transient. But if you have just regular mutable data structures, you can then ship them off, and it'll automatically ship that off so you can use it in the cluster. You can also use stuff in let bindings. You can combine parameters and let bindings together, create new stuff. You can define functions elsewhere in your code and then use that as your map function. This can be a function you define. It can be a Clojure core function. It doesn't matter. And then you can also use that within an anonymous function. You can use any type of Clojure function here is really the point. And the way that I'm doing this is the jar that actually goes off to Hadoop to run this code is an Uber jar containing all of your code. So when I reevaluate this function of x, I'm reevaluating it within the namespace you originally defined it in. So you have access to everything that you did there, including other namespaces. So if you want another library to use with your MapReduce jobs, just import that as you're generating your script, and it'll be there actually when you're computing data on the cluster. Lipstick is a library that we have at Netflix. It allows you to visualize Pig jobs specifically. Each one of the blocks on this screen here is an individual MapReduce job. You can see there's some commonality between there. The work that I was doing here was some clustering work, and I wanted to try out 3 different variations of the clustering. In Pig, it would have been very difficult. I probably would have ended up just writing the script 3 times and kind of tweaking it. In PigPen, this is a for loop. Each of those different 3 variants uses the same input data. So you can see where at the top, there's just kind of one starting point for the script. And then at that point, it branches out into our 3 different variants and then comes back at the end of the script to combine them together. The nice thing about PigPen is it allows you to manage very large amounts of complexity. This is another example of a script that I run. This one had a few hundred Hadoop jobs in here. You could feasibly write this in Pig or in another language. I don't know that you would ever want to, but in PigPen, this ends up being a couple hundred lines of code. I could take out big chunks of logic, shove in other chunks of logic into my script, and with a simple case statement, switch between them. I didn't have to worry about would my data match up, would anything else line up. A lot of the problems you would normally have when you're writing scripts. It's much more functional composition that you're thinking of when you're writing PigPen jobs, just as you would writing Clojure. Another tool that we have at Netflix is Genie. If any of you are using it, great. If not, you should go check it out. It makes cluster management really easy. There's a Leiningen plugin for PigPen that allows you a 1-line, you can submit your query to the cluster. This will send it off to Hadoop, package everything up for you, generate the script, do all of that legwork, and then Genie emails you when it's done. It is the simplest way to run MapReduce jobs. In the future, I want to get away from using Pig exclusively. It's been a great starting off point. Pig has done a lot of legwork in kind of optimizing joins and moving data around. There's a lot of stuff there that I didn't want to write from scratch, but we're looking into taking that abstract expression tree, running it on something like Spark or Storm, And for local mode, looking at core async instead of Rx, just as another alternative. And that's all I've got. Any questions?